Hi, welcome to another session of Basic Electrical and Electronics Engineering. Under class 3 of DC machines, we are going to see today different types of generators. If at all you are thorough with DC generators, then it would be easy for anyone to understand the types of DC motors. So this class would be very much interesting. So please follow what are the things we are going to discuss for different types of DC generators. Here you can see different arrangement of types of DC generators. For the first case, you can see a machine that is called as a DC machine is connected in series with some resistance, and the same machine in another picture it is connected parallel to resistance. And third case, you can see a series combination with the machine is connected parallel to another resistance. So how to designate these type of machines under DC generators is we are going to see in this class. So on the types of DC generators based upon the type of excitations, DC machines are classified as separately excited machines and self-excited machines. Whether it is motor or generator, this is a broad way of classifying DC machines. So a separately excited machines, here the field winding is provided with a separate DC source to supply the field current as shown in figure 1. You can see here there is a connection of the coil where you can treat this one as the primary of the circuit with a resistance of field, so it is termed as RF, and a machine is taken. Generally we designate the DC machine with M, where the connections you can see it is given like this. So in case of generator, we assume that the generator voltage is E suffix G, and the resistance of this machine is taken as armature resistance denoted by R suffix A. So this type of circuit arrangement or network arrangement can be regarded as separately excited machine. In fact, when we are talking about generator, it becomes generator, and when we are talking about motor, it becomes motor. Only certain specifications will change. When you're going to deal with motors, we are going to see what are those specifications which are going to change. Fine. Under self-excited machines, here the field current is driven by its own EMF generated across the armature terminals of DC machine. So depending upon the type of windings, self-excited machines are classified as series machine, shunt machine, compound machine. Whether it is case of generator or motor, this is a broad way of classifying self-excited machine. Another important factor, under compound machine, we have long shunt compound machine and short shunt compound machine. When you are dealing with generator, it becomes long shunt compound generator and short shunt compound generator. Whereas in the case of motor, it becomes long shunt compound motor, short shunt compound motor. Okay, we'll deal with the motor in the next class. First, let us see how these series, shunt, and compound machines are drawn under figure 2. So, a series machine where you have a series connection of resistance with machine, assuming the generated voltage in this machine, hence making the machine as generator. EG is obtained and it is connected. The machine is connected in series with resistance RSC. We also need to remember that the machine has its own armature resistance. Please keep that in your mind when you are going to see the derivation of the equations for current and voltage, how armature resistance is going to play its important role. Well, it is a series connection. In figure 2b, we can see the shunt connection where the generated voltage is Eg with internal armature resistance as Ra, and this machine is parallelly connected to shunt field. Sometimes it is regarded as R suffix F. Here it is designated as R suffix SH. So this is the shunt arrangement, and figure 2c represents the compound arrangement, whether it is long shunt, short shunt. We are going to see further. What we need to remember is that in the case of generator, the generator voltage would be Eg, having internal resistance Ra, that is connected in series with Rse, and this entire combination is connected parallel to RSH. So this is how broader classifications made under self-excited machines, that is series, shunt, and compound. Okay, in case of series generator, when you look at it, figure 3, from the basic circuit, we have seen the arrangement of series connection with the machine. Now I am connecting load to this machine. Now this becomes a closed circuit. The resistors of this closed circuit can be taken as internal resistance Ra, series resistance Rse, and load resistance RL. Fine. When the EMF, that is the induced voltage, is obtained in generator, it develops the current which is flowing through the closed circuit as Ia, since we have Ra, so that initially the current which is going to be obtained is Ia, that flows into the resistance Rse. So in fact this Ia is nothing but equivalent to Ise, because it's a series circuit. So whatever the current which is present in the closed circuit, whether it is armature current, series current, or load current, they will be one and the same. So once the current starts flowing into the circuit, the terminal voltage gets developed across the load. So in the series circuit, what you need to remember that the armature resistance, the armature current, the series current, and the load current are one and the same. Here we are treating as I. What is that I? When I'm going to apply KVL to this closed circuit like this, I'm going to obtain the current I. This I is equivalent to the equation 1 currents. So when the generator voltage is supplying the load, I'm applying KVL. So taking this voltage minus Eg from the bottom side. So it's a KVL application plus the current which is flowing in armature resistance. It is Ia. So multiplied with Ra becomes the drop at the machine. Then you have current which is flowing in RSC. So another drop will be obtained across this resistance. And in the load, when we have terminal voltage, which would be equivalent to ILRL, I am just replacing the ILRL with VT. So this is how you apply the KVL. Hence, the generator voltage would be equivalent to IARA plus ISCRSC plus VT. In fact, I can take IA equivalent to ISC. So total, I can take the value of current as I or IA, which is taking the combination of RA plus RSC plus VT. So this is the equation for series generator when we look at the circuit which is shown in figure 3. Let us go back to shunt generator connection. Now you see this is a shunt machine where on the left side you have field winding, on right side you have the load connected. Now current IA, it is obtained because of generated voltage, and at this particular node it is divided into two currents, that is IA equal to ISH plus IL. So that is how a shunt current is different from series current. So IA is equal to ISH plus IL. In fact, what is the ISH value? You can see this ISH is parallel combination with VT. So I can write ISH is equal to VT by RSH. I cannot write ISH is equal to EG by RA. Why? Because the generated voltage is going to be depend upon the self-excitation of the machine. Whereas the shunt connection VT is exactly parallel to this parallel circuit. Now EG would be the total voltage which is developed, and that voltage is supplying the entire external circuit. And that is why how we have taken the value of ISH, which is nothing but the parallel combination which is arranged to VT. Okay, now if at all I want to make the equation for generated voltage and terminal voltage, I'm going to apply KVL to this closed circuit on the left half, sorry, on the right half. So when I'm going to apply this KVL, I'm going to get minus EG plus IARA, the internal drop, plus VT equal to 0. Hence, EG would be equivalent to IARA plus VT. So this is how we frame the equation for generated voltage and terminal voltage with the help of equation 5. Now, based upon these analysis of series and shunt, we can easily estimate the equations for compound machine in the name of compound generator. Now, compound generator is divided into two halves, that is the long as well as short compound generator. Figure 5 represents long shunt arrangement, where you can see uh, the machine having its internal resistance is connected in series with series field winding, and this entire series arrangement connected parallel to a resistor that is connected in parallel. So we are treating that resistance value as RSH, and whatever the current which is going to be developed in machine, that is flowing through the series field winding. Hence here IA would be equivalent to ISC. Also IA is equal to ISH plus IL. When you apply KVL at this particular node, you are going to get the relationship between armature current, shunt field current and load current. So as I told you, IA is equal to ISC, and IA is nothing but is equal to ISH plus IL. In fact, ISC is equal to ISH plus IL. And what is ISH? As I told you, immediately you can see the parallel arrangement. VT is connected parallel to RSH. So ISH would be equivalent to VT by RSH. Fine. Now apply KVL to the external circuit. External circuit, you have this parameter, that is machine with series field winding, and you have terminal voltage. Hence minus EG plus IA RA of the drop which is having inside the machine, plus ISC RSC, the current which is flowing through the series field winding, plus terminal voltage is equivalent to 0. In fact, EG would be equivalent to IA times RA plus RSC plus VT. What we need to remember that the series field winding current and armature current are one and the same. So this gives us the another relationship between terminal voltage and generated voltage for long shunt arrangement. For short shunt arrangement, you can see the machine with its internal resistance is connected parallel to RSH, and this combination is connected in series with field winding, and in that series field winding is in series with low terminal. So here the equation again changes. So what we need to keep in our mind, that load current which is flowing through the load, it is equivalent to the series field winding current, and IA is nothing but it is equivalent to ISH plus IL. So this is the important factor we need to look into, the connection of figure 6. Fine. Now I'm applying KVL in anti-clockwise. You can see the direction of the loop we are taking anti-clockwise. Now with this, I'll be having minus VT, and ISC direction is in this direction. So the developed drop across this would be minus ISC RSC. You can see here minus VT minus ISC RSC plus this shunt current, it is flowing into the resistance RSH, and that is according to the our convention. So that is why it is in positive over here. So overall, I can obtain the value of ISH, which is will be equivalent to VT plus ISC RSC by RSH. So this is how you frame the equations for the connections of compound generator based upon the type of connection. So keep remember these formulas. In fact, the actual approach in order to solve different problems. In next class, we are going to see the problems which are involved with compound generator because it's a special case. Meanwhile, let us understand how a DC generator works. For that, I'm taking one example. A 4-pole DC generator with lab connected armature supplies a load of 80 amperes at 240 volts. The armature resistance is 0.98 ohms and the shunt field resistance is 60 ohms. We need to find here the total armature current, current per armature path and generated EMF. So this is the typical shunt generator what we have seen in our previous slides. So first take the data which is given. What is the data which is given? Here 4-pole machine, so P becomes 4. Input voltage is 240 volts, so V in is 240. The load current it is given as 80 amperes. Then armature resistance is 0.98 ohms. Shunt field resistance is 60 ohms. This is the data which is given. Please always carefully read the problem and collect the data which is given in the problem. Half of the problem will be solved by collecting the proper data. Fine. Now, total armature current for a shunt machine is nothing but Ia equivalent to ISH plus IL, right? And what is ISH? ISH, as I told you, it is nothing but terminal voltage divided by the resistance. So ISH is nothing but terminal voltage by the resistance. So in fact, here the voltage is 240 and resistance is 60. So this gives the value of ISH as 4 amperes. And the load current is 80 amperes. In fact, armature current, which is dependent upon this formula, changes to 84 amperes. So the total armature current of this particular shunt machine, in fact shunt generator, is 84 amperes. Next, current per armature. Since for lab connected machine, the number of parallel paths is equal to the number of poles, the current per armature would be equivalent to 84 divided by 4. 84 is the armature current. We require armature current per armature, so it will be 84 by the pole of the machine, that is 4. So this gives the current per armature as 21 amperes. Then the generated EMF. So the generated EMF is given as Eg is equal to Ia Ra plus Vt. What is Ia? We got 84. What is Ra? That is 0.98. What is Vt? Vt is 240. So here it is V in, or we are taking the value of terminal voltage as 240. Keep that in mind. And this gives us the value of generated voltage, which will be equivalent to 322.32. It is not amperes, it is volts. I have overlooked this equation, but it is the value of voltage. It is 332.32 and the unit is volts. So please forgive for this small mistake. Here it should be, V. So 322.32 volts. Okay. Okay. Now if the same machine is having wave connected armature, then the parameters which are not going to alter is these parameters. And for wave winding, we are going to get the current per armature, which will be equivalent to 84 by 2, because here parallel path is not equivalent to number of poles. Here for wave winding, parallel path is fixed, that is 2. So current per armature would be 42 amperes. Whereas the generated voltage here, again it would be 322.32 volts. Is this clear? Fine. Now let us go with the next problem. Again, we are taking the shunt machine here, but see the parameters what it is showing here. The armature of a 4-pole lap-on shunt generator has 160 slots with 4 conductors per slot. The flux per pole is 0.08 Webers. If the armature resistance and shunt field resistance are 0.02 ohms and 20 ohms respectively, then estimate the speed of the machine when it is supplying a current of 110 amperes at terminal voltage 240 volts. So here we need to find out the speed. Now what we are going to see, the data which is given, that is number of poles is 4, terminal voltage is 240, load current is 110 amperes, armature resistance 0.02 ohms, shunt field resistance 20 ohms. And another important parameter which is given as flux, that is 0.08 Webers. So this is the data which is given in the problem. Now you know that shunt field current is obtained as terminal voltage by RSH, so it is here 12 amperes. And we also know that armature current is equal to shunt field current plus load current. So here the value of armature current would be 122 amperes. Now since EG is equal to IARA plus BT, we are going to get the value of EG as 242.44 volts, and we need to estimate speed. For that, the number of slots on armature which is given as 160, conductors per slot it is given as 4. So total number of conductors on armature will be given as Z is equal to 160 multiplied with conductors per slot. So 160 multiplied with 4 will give you the value as 640. Now that is the value of Z. Since we are having this lab connected network, here we need to remember that number of poles is equal to number of parallel paths, which is nothing but equivalent to 4. Now the generated voltage formula is given by EG is equal to 5 PNZ by 60 into A, and from this formula we need to estimate speed. So EG value we have obtained as 242.44, phi is 0.08 Webers, P is 4, N we are supposed to find out here, Z is 640, 60 multiplied with A is 4. So just I'm substituting the values in the formula. So this is what I'm going to get. Now with this calculation, you can easily observe that this 4 will cancel out. Okay, and 242.4 can be multiplied with 60 whole divided by 640 multiplied with 0.8. This will give you the value as the value would be around, sorry, the cursors are working. The value of N would be equivalent to 284 RPM. So this is how you calculate the value of speed for the machine. So I hope you have understood the basic way to solve the problem for different types of generators, framing the equations, finding out the value of generator voltage in terms of terminal voltage, developing the current equations. So this would be easy for you to understand the different ways of finding out the different numericals for the given system. I hope you like this video. Please share and subscribe to my channel, and please be in touch with the channel by pressing the bell icon. Have a good day. Bye bye.